Bismillahirrahmanirrahim. Hello students, welcome to the Electrical Engineering channel. In this lecture, I am going to explain the electric field intensity. So electric field is basically the field due to a static charge, and electric field intensity can be defined as the electrostatic force per unit charge. So in order to derive the mathematical expression for electric field intensity, we have to consider two charges, and one of those charges is actually a source charge, and the second charge is called a test charge. Now the source charge, which is Q1 in this figure, is actually responsible for the creation of electric field, and in order to sense the intensity of this electric field due to this source charge Q1, we have to use another charge. That charge is called as test charge, and if we place a test charge around the source charge, that test charge will experience an electrostatic force. Now the force experienced by this test charge divided by the magnitude of this test charge is actually the definition of electric field intensity. So its mathematical expression can be found out by using the expression for the electrostatic Coulomb's force. So here Q1 is considered as a source charge, and Q2 is a Qt is basically a test charge, and force on this test charge Qt is actually equal to Ft equal to q1 qt divided by 4 pi epsilon r1t square into a1t. R1t is the distance between the charge q1 and qt, and a1t is the unit vector directed from q1 to qt. Now, if the magnitude of this test charge is assumed as unity or 1 coulomb, then the force divided by this Qt will be equal to Q1 over 4 pi epsilon R1t square into A1t. And this is the definition of the electric field intensity. And this is the electric field due to a source charge, which is Q1. So E is equal to, in general, Q over 4 pi epsilon R square AR. And R is actually the distance of the test point from the source charge, and the direction of electric field intensity due to the point charge is radially outward from the source charge. So this is the expression for the electric field intensity due to a point charge, and it is in the direction of AR. So AR is same as we used in spherical coordinate system, and in spherical coordinate system AR was originated radially outward from the origin, and here it will be radially outward from the source charge, which is q1. So we have to use the same unit vector, and if we want to convert this expression into Cartesian components, then we have to use the expressions for this r and ar. So E is equal to 4 pi q over 4 pi epsilon. R square is equal to x square plus y square plus z square. And AR is equal to R vector divided by R magnitude. And R vector is equal to x ax plus y ay plus z az. And R magnitude is equal to x square plus y square plus z square under root. So this expression will have all the three Cartesian components. So if the test charge is placed at the origin, then we will use this expression. But if the source charge is placed at any point other than the origin, then this will be the scenario. So this is the origin, this is the position of the source charge, and this is the point at which we want to calculate the electric field intensity. Now, the position vector of the source charge is represented by r dash, and its components in Cartesian will be x dash, y dash, and z dash. And the position or the point at which we want to calculate the electric field intensity is this point, and its coordinates are x, y, z, and its position vector is r. So the vector directed from the source charge to the test point is actually r minus r dash. So here we have to use uh, r minus r dash and r minus r dash unit vector in this expression. So it will become r minus r dash magnitude square, and r minus r dash vector divided by r minus r dash magnitude, and it will become q over 4 pi epsilon r minus r dash vector divided by r minus r dash magnitude cube. So this is very simple to convert these position vectors into Cartesian components, and this expression will become x minus x dash square plus y minus y dash square plus z minus z dash square under root and its cube. So under root will become 1 by 2. So its power will be 3 by 2. And the same components will be used in the numerator term along with their corresponding unit vector. So it will become x minus x dash ax plus y minus y dash ay and plus z minus z dash az. And we have to remember that x dash, y dash, and z dash are the components of the source charge, and x, y, and z are the components of the test point or at the point or the point where we want to calculate the electric field. Now, if we have two charges Q1 and Q2, then the total electric field due to these two source charges will be the sum of electric field due to individual charges. So it will be equal to Q over 4 pi epsilon 1 minus R1 magnitude square R minus R1 divided by R minus R1 magnitude. Similar expression for the second source charge Q2. Similarly, the electric field due to n charges will be the sum of the electric field due to the individual charges. So we have to use the summation term over here, and it will be m minus 1 equal m equal to 1 to n qm over 4 pi epsilon r minus rm divided by r minus rm magnitude cube. Now we are going to solve an example, and after solving this example, we will be very much clear in calculating the electric field due to two charges. So we have 2 point charges. One charge is negative and it is placed at this point 25 minus 30 and 15. Second charge is Q2, its magnitude is 0.5 microcoulomb and it is placed at V minus 10, 8, 12. So these components are given in centimeters. So we have to use the expression accordingly. So we have to convert these quantities into SI units. So here we have two parts of this example. In the first part, we have to calculate the electric field at origin, and in the B part, we have to calculate the electric field at this point. So for the first part, R will be equal to 0, 0, 0. R1 will be equal to 25 minus 30, 15, and R2 will be equal to minus 10, 8, 12. Now E is equal to Q1 over 4 pi epsilon uh, R minus R1 vector divided by R minus R1 magnitude cube. So it will become 25 square plus 30 square plus 15 square because the one point is origin. So 0 minus 25 and 0 plus 30 and 0 minus 15. They will all become positive, and we will have to use squares, and the power is 3 by 2. And in the numerator term, we have to use the same components. So 0 minus 25, 0 plus 30, and 0 minus 15 AZ. So this is the expression for electric field due to first charge, and due to second charge, it will be evaluated in a similar fashion. So 0.5 into 10 to power minus 6 divided by 4 pi epsilon, and 0 plus 10 square plus 0 minus 8 square plus 0 minus 12 square, and here 0 minus 10, 0 plus 0 plus 10, 0 minus 8, and 0 minus 12 is. So after evaluating both these expressions, we will get the final answer as 9.2471 AX minus 7.766 AY minus 9.437 AZ. Now, since we have used the position vectors in centimeters, and we know that in this electric field expression, the R square independence is present. So we are actually dividing the square of the position vectors here. So we have to now consider 1 over centimeter square by uh, so we have to use 1 over centimeter square to convert to the SI units, which is meter. So 1 over centimeter square is equal to 1 over 10 raised to power minus 4 meter square, or 1 over centimeter square is equal to 10 raised to power 4 per meter square due to the 1 over r square dependence. So it will become 10 raised to power minus 10 raised to power 4 over here. So here we will get the expression in volts per meter, and it can be written as 92.25 AX minus 77.66 AY minus 94.37 AZ, and it is 10 to 3 volts per meter, so it will become kilovolts per meter. So this was the first part, and the second part will also be solved in a similar way, And in the second part, again, we have to calculate the electric field intensity due to first charge and due to the second charge. So this is the first charge, and in the second part, I have actually converted the position vectors from centimeters to meters. So it will become 0.25, it will become minus 0.3, it will become 0.15, and it is 0.1, 0.08, and 0.12. So if I use this convention in the second part, then this is the final expression that I get. And after doing all the calculations, the final electric field intensity is calculated as shown here. So that is all about the definition and explanation of electric field intensity due to a point charge. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.